Pleasure to welcome Pedro back to AS. Give a huge talk, now greatest. And we take Pedro to dinner. We use the same algorithm. If you want to join us, please send me an email before 4 so that I can make a reservation.
Thanks a lot, Nadia. Thank you so much for the invitation. It's a huge pleasure to be here as usual. It's the first time I come where the weather is worse here than in Waterloo. Never, ever.
It's a special case of more general facts about the countries. You know that.
This was a surprise. I've always shocked with all
Even without the word weather.
Yes.
Yeah. Really, I'm really happy also. I mean, yesterday when I was going through security, I noticed I did not have my passport. I had left the passport in the bus. I managed to run. The bus was leaving the airport. I was calling it. It stopped. I got in the bus and I got the passport and I made it in time. So I feel really super, super lucky that it was not a huge disaster by a few seconds. Yeah.
We are the lucky ones.
So great. So I'll tell you about some work that we did, and mostly about things that we are thinking on with Arish, who is in the audience, and Andrea Guerrieri, on trying to understand huge operators. And basically what I would like to do is to spend a few minutes on slides just with some very general blah blah about ADS-CFT, huge operators, things that we know well, a bit to set up the context and the motivation. Then eventually a plot will show up. It will be this plot, but in a reasonable size so that you can see what this is. And then I'll switch to the blackboard and I will explain exactly how to derive the various features of this plot. It's a cute computation, a simple computation in matrix models, and that will take most of the time. And then we come back for the slides and try to see what does this computation teach us, what did we learn about all this grandiose, all this bigger picture motivation in the beginning. Okay, so that's my plan. So it's not a huge talk. As you see, it's a 60-minute talk, very bounded. Okay, so there are some examples of holography where we have a good understanding of what's going on and how some theories admit a gravity dual. So there are many examples of theories that we conjecture to have a gravity dual. N=4 super M-mill is the most famous. Then we have BFSS matrix models and their mass deformations. We have IKKT matrix models and their mass deformations. And they are all very similar for the purpose of what we are discussing today. You can think they are all more or less like N=4. N=4, we have 4 dimensions, some scalars, some commutators, some fermions, and so on. Quantum mechanics, you throw away space, and IKKT, you throw away space and time. And you get a 0-dimensional matrix model with some matrices X, Y, some commutators, and so on. So N=4 we understand well. So in N=4, we understand that gravity emerges because of a decoupling of everything else. So we understand that in N=4, operators gives us states, and strings, for example, are the state operators that have dimensions of order 1, that don't scale with n. They are dimensions of order n to the 0, like, for example, a word like xy, xy, and so on. So this would be dual to a string. And then these words that describe strings in N=4, some of them, for example, when I take symmetric combinations of x and y, their energies are just equal to the classical energy. Like in this case, it will be 4, and it stays 4. So those are the BPS states, the BPS strings, and they correspond to the gravitons and the Kaluza-Klein modes of the gravitons. And so those are well understood. In the beginning of ADS-CFT, many checks were done of these operators. They stay order 1. Then we have things that are not symmetric. We can have a bunch of words, and we start inserting, say, these commutators inside the word. So we have, say, x, x, y, y, and then we start putting commutators. So instead of doing fully symmetric permutations, we start putting these commutators. The simplest example is the Konishi operator. That is just this commutator square, for example. Now, when you put these commutators, then in this string of words, what happens is that now, instead of a BPS state, you get a non-BPS state. So you can think that you had your string that was a very small point-like string, and putting a little bit of this commutator is like inserting a bit of string, giving the string some size, and now it's no longer BPS. The commutator, the order matters. I mean, it's a commutator. So each non-commutativity that you put here inside the commutator makes the operator non-BPS. And intuitively, you could imagine that if you go to strong coupling, it's a bit like putting many of these guys, the dimension could become very big. Now, this is, of course, super hand-waving, but that's what integrability makes rigorous. Integrability says, indeed, that's more or less what happens. If you study the spectrum of operators, you see that some operators, the dimension is 0, but the other ones that they are not 0, they start growing, and they grow, and indeed, they grow very much so that they decouple. And because they decouple, when we go to strong coupling, they go away. What remains are the massless ones, which are gravity. And so at least we have some kind of qualitative understanding and quantitative when we use integrability of what's going on. Now, and then for the lower you go, the simpler naively the model becomes, but the less we understand about these models and about how precisely this is realized in the other models. We expect it to be similar in this VFSS matrix quantum mechanics. For example, again, we can put operators, and again, some will be BPS and some will be decoupled, and so on. But which ones are which and so on, it's much less well understood. Now, this is not the full story. So like these light operators, these words are strings, as we know, but there are other things that are not just trace of xy or x squared or trace of x squared. There are things that we call they are heavier. So this, we have these light operators that we just discussed with order n to the 0. Example, trace of x squared, like a small BPS string. It could be trace of x squared times trace of x squared, so like two small strings. But okay, dimensions of order 1. Then you can have dimensions of order n. For example, determinant of x. And those would correspond, say, to a D-brane, for example. So it's heavy, but it's not that heavy in the sense that it's still a probe. I put a D-brane in the geometry, I find where the D-brane goes, but it doesn't deform the geometry. And then we have very big operators, like determinant of x to the power n. So it has order n square fields. Those really change the vacuum. So it's really like hitting a table with a hammer so that the table becomes warm. Right? It's really, you are doing some very strong action that is back reacting and changing the vacuum. So those are, they move us from the vacuum, they move us to a new vacuum. And so examples of computations we can consider is we have some theory, and we consider light probes in the presence of these huge operators that deform the vacuum. So we could put some very big operator, like these determinants to the n or something. Typically, we put a cat and a bra to create the state and annihilate at plus and minus infinity. And then these light correlation functions in the presence of huge operator are like probes that measure this geometry. Now, the precise map between very big operators and very deformed geometries is hard, of course. Sometimes it's well understood, for example, for half BPS operators, we have a good understanding of, given a very big operator, what kind of geometry does it give. But in general, if you go to other examples like 1/4, 1/8, 1/16 BPS, my understanding is that we know much less about them. There are people trying to understand aspects of the geometry, aspects of the field theory, but way less is understood. We don't have a clean map as far as I understand, but if I'm wrong, please, we would love to know about it. Between here is a very big 1/8 BPS operator, here is the corresponding dual geometries. Some things are known, but the full story is a bit incomplete. And of course, that's just the tip of the iceberg. Then there are the non-BPS operators, many more of them. And there are a ton of them. I could write some determinant of XX bar to some huge power and try to normalize that operator. It's a mess, it's a complicated thing. There are many more of those operators. And typically a generic one, we would say probably should be some kind of black hole state. It should be, it's the majority of such states. Now, obviously, this is hard. So that the LLMs geometries with 1/2 BPS were easy, but very special. And the more you go towards these non-BPS operators, it's hard for the usual reason where quantum theory for very excited states are hard. Scales, thermalization, and you more or less know what you expect. But computing explicitly, it's usually very hard. It's computationally very complicated. But what I find amusing is that, well, it can be hard, but at least it's well defined, right? So what does it mean to study some quantum geometry or something? Means studying operators with big dimensions. It's not something fancy about Alice's and dogs and observers and so on. I mean, it's very concrete. It's really take the operators whose dimension is big. Okay? And the hope is that there could be interesting information about quantum gravity by looking at that subsector of conformal field theory. I mean, is a black hole, say, one of these huge operators, or do I need to take many of them, or a coherent state of them? Or does it matter when we put probes in the presence of a heavy operator? How sensitive are the probes to the detail of the heavy operator? Not at all, or a little bit? When we say a little bit, is it 1/n? It's exponentially n? What is it? So at least it tries to be very concrete if we phrase it in gauge theory language. So that's the general hope. Okay. So just repeating what I said, typically when we consider the light operator in the spread, so one thing we can consider are these light probes in the presence of huge operators. And that's typically what we do to test conjectures. So when, for example, Lin, Lun, and Maldacena suggested what would be the dual of this 1/2 PPS operators, it was important to test this idea, and Skandaris and Taylor, for example, computed many probes of these light operators in this conjecture dual, and they checked indeed it matches what the gauge theory gives. So these are the typical types of probes that are very important to test whether your picture is correct or not. Now, when you compute probes in LLM geometries, you get results that are not universal. What I mean by this is that you take different LLM geometries, you get different results. And that is a feature, it's not a bug. It is just that these geometries have lots of structures. They don't have horizons, they are parameterized by some very rich data of black and white regions. And so they have lots of information, and indeed different geometries give different results for these probes that you put them on. If we could do some computation for non-BPS operators that should be dual to some black holes, which is harder, we expect, on the contrary, to find universality. We would expect that I don't care very much what particular microstate of the black hole I take. It should be characterized by a few macroscopic quantum numbers, and then the precise details of the operator should not matter. And so it would be nice to find in what time models do I find this transition from universality to non-universality? How do I find that, especially when we go to strong coupling, that some universal sector emerges? And so that led us to go back and try. So we studied a bit some huge operators in n = 4 in the BPS sector. We were studying some 3-point functions and so on, and finding this very rich behavior. But we were trying then to look for something more universal. So we thought of going to this so-called Hoppe model. So you see that, I mean, it's kind of easy to understand why we would end up here. So what did we want? We wanted to have some kind of toy model. We want big matrices. Matrices are very important. I mean, if you want something that resembles some kind of holographic dual, big matrices seems to have a good idea. We want to have an action similar to the action of n = 4 or IKKT and so on. So with some coupling that we will play with. We want to have these huge and big operators and light operators that would be traces and determinants of these two matrices. So we decided to study this so-called Hoppe model. It was a model that, if you don't have these huge operators here, it was solved in beautiful papers by Hoppe in '89 and by Kostov, Kazakov, and Nekrasov at Finite N in '98. And there is also a beautiful paper that I should highlight by Berenstein, Hanada, and Hartnoll, who understood what is the right language for studying this model, again, for the vacuum, when you are considering strong coupling direct. If you solve it without the simplicity of strong coupling, you get some elliptic solution, and the solution is in terms of elliptic functions. It's solvable, but it's hard. At strong coupling, things simplify dramatically. Okay, so that was the motivation. So this is the basic motivation why we end up studying this model, is trying to start with this landscape of possible holographic models and trying to find a toy model that might still capture some of these features that we are after, but that is in the border between integrable and non-integrable models that we might still be able to compute something. And these computations, you could organize them by difficulty level. They never reach very difficult because it's a matrix model. So it's still all within the relatively easy stuff, like when you have these recipes and you are cooking and you have from all the way from, I don't know what's the hardest there. Okay. So you have some difficulty level, and what I will start in the blackboard is with the simplest possible examples, where let's take some huge operator and some light operator that depend on one of the two matrices, and that will simplify our computations quite a bit. And so I'll start with this in the blackboard, then we will discuss these two cases back with the slides, and in particular, when we go to these cases, it's not like things are much more complicated, but we don't know how to solve analytically, and we used hybrid Monte Carlo, some simple numerical technique that people develop for studying this matrix model. So this stuff, this part is totally analytical, part of this is analytical, and this is fully numerical. Okay, with some analytic conjectures that we check numerics. So again, to be precise, here is an example. We could have some huge operator that could be, for example, exponential of some classical source dot your matrix. This classical source could, for example, be some n diagonal matrix with elements going from -1/2 to α/2. So a source that's like a line source with eigenvalues from -1/2 to α/2. Just to be a concrete example. And this light probe could be some moments of the matrix X, like trace X squared or trace X plus. Okay. So I hope it's well defined. So let me then show you the finally. So this is the plot that we get. Okay. So let's just stare a little bit at the plot, and then I'll show you the computations that are very simple that lead to this plot. So here it is. So what we are plotting here in this two matrix model, the matrix model is written on top. It's some ratio of the moment 4 over moment 2 squared, just to be well normalized. Okay, so we compute moment 4 over moment 2 squared. That's what is the y-axis. The x-axis is roughly the size of the operator, is how big is this source. It's this alpha, and the source goes from -1/2 to α/2, and alpha can go from 0 to 12 in this example. And then we have many curves corresponding to different couplings. All the way from zero coupling, where you can drop the commutator square, and you get a free Gaussian matrix model, to lambda equal 15,000. And this plot was done with n equal 1,000. Okay, so it was done, we had 1,000 by 1,000 matrices, couplings from 0 to 15,000, and here is the plot with what we get. And clearly, let me just highlight this plot has a couple of features. Lines asymptote to some funny value, that is around 1.8. At weak coupling, it goes from 2 to to this asymptotic value. And if we are at weak coupling or intermediate coupling, things change smoothly with alpha. But if we go to strong coupling, as the curves go to strong coupling, you see that they approach a universal region. There is a plateau where things are universal, and then there is a phase transition at some critical value when things change to this region. Okay? So those are the various features we have here. There is a universal phase, there is a phase transition, and there are a bunch of asymptotes and some different regimes of this matrix model.
There's no universality at large alpha?
And at large alpha, all curves seem to approach the same thing, so there's also some universality at large alpha. So there's also universality at large alpha and universality at strong coupling. The universality at large alpha it's okay, it's nice, but it's not the most interesting one. I think the strong coupling one is more interesting. Okay, so 20 minutes. Okay, so that was 5 more than expected, and now we go to the blackboard. Okay, are the lights okay for people to see in the blackboard? Okay, and I will raise the projector in a second. Maybe I'll do it now. Okay. Okay. So again, let's set up this computation where I want to compute some simple correlation function like this in some 2D matrix model. So what I'm doing is I'm integrating over the n square components of x, the n square components of y, raised of x to the n, times Then I have the huge operator. I want to compute it in the presence of some huge operator, the huge operator, the exponential n raised of x dot some source. And then we have the action exponential of minus n raised. So the first thing, so this model, you see, it's kind of easy to study because there are two things that are happening here. So the first one is that y appears just in a Gaussian way. So that's why putting operators that don't depend on y makes it very easy to integrate out y. So y appears in a Gaussian way. And here we have an external, we have the coupling of a source to x, but there is a beautiful integration by Ari, Chandra, Itzikson, and Zuber that we can use, that the integration over the angle between two matrices so if you have some integration over the angles of these two matrices, this is equal to the determinant of the eigenvalues of xi times the eigenvalues of xj over I and j divided by the van der Monte of x. The Monte of x is just product xi minus xj. It's also a determinant. Okay, so this is an exact result. There's no approximation. If you take 5 by 5 matrices, you get a 5 by 5 determinant. Okay? So it is just. There is a beautiful result, which is that this determinant has a beautiful large n limit. I'm not going to discuss, but I'm going to just advertise that this exists. That when n goes to infinity, this becomes the exponential of some action of a 1 plus 1 dimensional fluid. Okay? It's really something very simple, but very non-trivial, that if you have a fluid which has a density that is the density of this axis, and then you have at some time t equals 0, and then at time t equals 1, the fluid density is the density of the j's. Then the action of the fluid as it goes in 1 unit of time from x to j, it's what computes the large n limit of this determinant. So it's just a true statement. Forget about everything in the blackboard. There is such an equality. This determinant is equal to a fluid. You could forget matrix models, forget everything. It's just a true statement with a particular equation of state and so on.
Is lambda on your slide exactly the same as G or is it G times N?
Yeah. I could try to, but I would not be able to. Yeah, this is the same as G.
It's not G times N.
No. It's exactly G. It is just, yeah, lambda is G. Apologies. Yeah. Okay, good. So that's it. So now immediately we can see that because y is Gaussian, x we can easily integrate out. So we can go to the eigenvalues of x. Once we go to the eigenvalues of x, y is trivial to integrate. And so let me write immediately the result. We go to the eigenvalues of x. We have dx1 up to dxn. Trace of x to the n is just eigenvalue x1 to the n plus x2 plus x3, but those all give the same thing, so it cancels just the 1 over n, nothing more. Then we have exponential of minus n over 2 sum over I xi squared. That comes from the Gaussian, just the Gaussian part. Then we have the van der Monte. That is what happens when you get the measure, when you go from eigenvalues, when you go from matrices to eigenvalues, you pay this van der Monte. But this van der Monte comes with a lambda, which is equal to G. I will not try to, sometimes lambda will be lambda, sometimes it will be G, which is the following, it's product xi minus xj squared. That's the usual van der Monte. But because we integrated y there, we get this. You can tell me if you see it. So this came from integrating out the y's there. So they came with this 1 plus g xi minus xj squared. And so we have this product over I smaller than j. And then we have determinant of e to the n xi j divided by Vandermonde of the x. Where Vandermonde of the x is what I wrote there, which is just this with lambda equals 0. Okay. So this is the result. And again, it's important to stress that here we have the probe, and the rest is the huge, the action plus the huge operator, and the huge operator changes me to a new background. So you can think of the rest is e to the minus a new action because of the huge that is deformed by this j because of the huge operator. Okay? And of course, this result, okay, if you want to normalize, you divide by the same thing with x to the without the probe. And this is just equal to what? This probe determines some density of eigenvalues, rho of x, and then you just integrate the moment this probe, and you get this, where this solves the saddle point equations from this trivial action here. Okay, so usual stuff with matrix models, and not to bore us, I wrote the equation here beforehand. Okay, so here is the saddle point equation. Can you see? It's not obscured by the computer, so it's very trivial to see where it comes from. So the Gaussian gives the first term. That integral here with a slash comes from the derivative of this effective Vandermonde. So you take derivative of this, you get some kind of Coulomb force log, and the Coulomb potential, and the derivative gives this 1 over x minus y. That's the usual Vandermonde. There is an extra term from the denominator, so you get some effective sum. It's a product over I smaller than j, which translates into j not equal to y, which is this principal part integration here. And then you have this part here, and this part here. This simplifies for j linear. So if j is equally spaced between minus alpha over 2 and alpha over 2, then effectively this thing here, in this case, becomes some Vandermonde of e to the alpha x, right? Because it is just, you see that it is just e to the x times j. But that was the same as x to the j, if I put the x upstairs, right? So that's just Vandermonde of exponential instead of Vandermonde of x. Okay? And so because it's Vandermonde, it's a simple product as well in this case. So in this toy model, where the source is linear, you can take the derivative, the variation of the huge operator very explicitly, and you get this saddle point equation.
Sorry, what is alpha? I missed that.
Alpha was the source, this source j, linear, this linear source was going from minus alpha over 2 all the way to alpha over 2. Okay? So basically this j is minus alpha over 2 plus j times alpha over n. Okay, so it goes linearly from j equal 1 to n, all the way from minus alpha over 2 to alpha over 2. Like putting some constant, some homogeneous source. Okay, some line source for this over. Okay, good. So this is the general stuff, the general treatment we get. This equation is complicated to solve. As I said, if alpha is equal to 0, you drop this part here. This equation is still complicated to solve, but you can solve it. It's given by some elliptic functions and so on. That's what Kazakov, Kostov, and Hoppe and Nekrasov solved many years ago. Okay, so now let me just point out how you would go about solving this in various limits. So the first one would be weak coupling, and weak coupling, I'm not going to bother people with a trivial weak coupling computation, so let me just point out, if there is no coupling here, you don't even go to eigenvalues or anything, the integral is just Gaussian, so you immediately write down that, let me write here, so at coupling equal to 0, of course the integral is Gaussian, so expectation values of trace of x, y, etc. are just obtained by derivative with respect to sources of some exponentials, right? So you can compute this again exactly when the coupling is 0, you compute this ratio exactly, there's no approximation here. And then again, when the source is linearly spaced between minus alpha over 2 and alpha over 2, you just compute these averages explicitly, and you get this result, which is some curve that goes from 2 to 1.8 as you interpolate from alpha equal to 0 to very big alpha. And that was the purple curve in the plot, the one with 0 coupling. So let me highlight that this is an example where here we have no source. Here we have huge source when alpha goes to infinity. And the distributions that we get, even though the result is very trivial, the solution to this equation when lambda equal to 0, we don't know how to solve this analytically. So we know how to compute the moments, but if you just take lambda equals 0, solve this equation, we actually did not manage to solve it. But we know qualitatively what's happening is that the density goes from semicircle. So it's some funny density that is semicircle at alpha equal to 0, because alpha equal to 0 is just, there's no source, there's no lambda, so it's just free Gaussian matrix model, so it's Wigner's semicircle. And as alpha goes to infinity, it becomes a constant distribution with size 1 over alpha from minus alpha over 2 alpha over 2. So it's some distribution that interpolates between the two that goes between Wigner's semicircle and constant distribution. And in particular, this constant distribution, you see that this distribution is nothing but the distribution for the source J. Right? The source J was equally spaced from minus alpha over 2 and alpha over 2. So what is happening is that when the source is very big, it's attracting the eigenvalues and they go to the source. Okay? So that is the universality that you asked about. Very large sources, it seems like the sources attract the eigenvalues and the eigenvalues tend to go to the source. Okay. Good. So this was the story at weak coupling. So at weak coupling, nothing is universal. Things are explicit. You can compute them. You could now do perturbation theory. It's easy, but there's nothing universal here. So next, let's go then to strong coupling. So lambda equal infinity. And let's see what would happen in this model at very strong coupling. Okay, so let's go to this model and now go to very strong coupling. And first we can even study no source. So let's first recall what happens when alpha equal to 0. Okay, so there's no source, so forget about this last term. And you have this term here, and lambda is very big. Okay, so first thing you do, if lambda is very big, I drop this term and I get something that doesn't make sense. Of course, now let's do it more carefully. So what is happening is, of course, that when lambda is very big, this tells me that x and y need to be very small to compensate for this. So things are localized. Indeed, if it was not for this term, x minus y, this, when lambda is very big, would be just a delta function. That will tell you that this is localized. Now, because there is this x minus y, it's not a delta function, but it's almost a delta function. It's a derivative of delta function. So what you get is something like minus x minus 2 pi over square root lambda times rho prime of x equal to 0. Let me fix factors of 2 pi that probably are wrong. While you yeah.
Sorry, what's the relation between the two terms here? We take both or just one? In the cell point equation.
So this comes from the source. This came because there was a huge operator. Yeah. Was that your question? What's the origin of these terms?
So do you take it into account there or not?
I'm dropping this term because I'm setting alpha to 0, and I'm saying that this dashed part is equal to the rho prime. So when lambda goes to infinity, that integral there, what I highlighted there, simplifies to this. Okay? It's easy to see that when lambda is very big, this is what it does. Well, but then, okay, this is rho prime, so what this tells you is that rho of x is not semicircle, it's not constant, it's a parabola. So it tells you that rho of x is L squared minus x squared divided by 4L cubed over 3. So this is a parabola from minus L and L. You see the derivative where L is equal. You can work out, just compute the derivative, but I'll stop it so that I don't write mistakes. Where this L, which is this L for vacuum, why vacuum? Because we are going alpha equal to 0, is some funny number, 3 pi to the 1/3 over 2 lambda to the 1/6. And what's important to highlight that we had seen before is that this is very small. Right? So it's a very small, very thin, very high parabola. So it's a very peaked parabola with size L, where L decays with this lambda. You see that it has this funny power, lambda to the 1/6. That's why in practice, when you do numerics, it's very hard to go to large lambda, right? You take lambda to the 10 to the 6, which is 1/10. So you really need huge lambda. And then if you have to do huge lambda, you can go, let me put 10 million. But then you need to be in the tooth limit. So then n needs to be huge. So there's no way you cannot put 10 million. So if you want to put a reasonable n, there's a reasonable lambda that you can go to. So these models are challenging to study at strong couplings. Okay, fine. So we compute this parabola. And now that you have this parabola, you can ask for a parabola, what is the moment x to the 4 divided by the square of the moment of this moment. For a parabola, you just integrate a parabola with x to the 4 divided by x squared, and this is 15 over 7. And so that plateau that you saw there, where the curves at strong coupling were all going there, was exactly this 15 over 7. Then these curves that were going there were doing something like this, and there was a transition. This was alpha. Okay, so this plateau here, alpha, this was alpha equals 0, was what we just derived. Okay, so that was alpha equal to 0. And this was in this beautiful paper by Berenstein and Hanada, most of this. Now, you can do alpha not equal to 0. Now, when alpha is not equal to 0, now we could be a bit experimentalists. We saw this plot and we saw there was some universality. All strong coupling curves were going to the same thing. So what must be the explanation? Even when alpha is not 0, they must all be parabolic. I mean, it must be. Okay, so let's try. So we try an ansatz where we say rho of x is equal to this. And then you plug that rho of x in this expression. And you evaluate this term with that rho of x. And you evaluate this now with alpha. And you evaluate this full thing with that rho of x. And what this gives you is that this thing with that rho of x becomes equal to alpha squared over 12 plus L vacuum cube over L cube times x plus corrections. Corrections in negative powers of lambda, suppress that strong coupling. Okay? So basically, you plug this parabola, and indeed you got that this full thing was something times x. So now to solve the equation, all you do is you set this to be equal to 1.
Seems to me, I misunderstood something. This is not an ansatz. This is, you're just doing perturbation theory in alpha.
No, not perturbation theory. I'm solving it now at finite alpha.
Right.
I'm saying Let me take rho to be a parabola, and I plug a parabola here.
But wouldn't you get the same thing if we just work perturbatively in alpha? You first solve the
If
problem.
you did perturbatively, you could see that to leading order in alpha, it's still a parabola. But I don't want leading order in alpha. I want alpha equal 1/5. I don't want small alpha. I want alpha equal 0, and then I want to show there is a plateau. It's not about the first correction to alpha. I want to see it's really always a parabola. So I pick a parabola, I plug the parabola here. I do this integral, and I get a number times x. That's not trivial. It could be a number times x cubed. It could be a number times x to the 4, but it's a number times x. Oh, then I just say set this number to be equal to 1 to cancel this time.
You just managed to solve the saddle point.
You just solve the saddle point equation. And so the saddle point equation tells me that this indeed works, and it tells me that L is equal to L of the vacuum divided by 1 minus alpha squared over 12 to the power 1 cubed. 1/3. Okay, you just solve that equation. And so it tells you, now it explains what's going on. It tells you that indeed there is some big region up to some alpha critical, which is 1/12, 1/square root of 12, where this can hold. And in that finite range, you better get this universal result. And then when alpha is bigger, there is a transition to some other solution at the saddle point that we need to find. Okay? And that would be the challenge, find this other solution. Okay? We did not manage to. So I will show you numerically, because numerically we can of course solve it. So we will see what it is. But this explains this part of the plot. There is this universal risk, and then a transition to something non-universal for bigger alpha. Okay, finally to conclude before going to slides, I know there are 2 more things I want to show. So then we could also do finally to complete our understanding of this plot, we could try to understand large sources. So what could be the intuition for large sources? So you have an integral like that. You could imagine put jx and jy, put sources in x and y direction, and now suppose x and y, the sources are big. Okay? So if the sources are big, what do we expect? We expect that we should be able to do semi-classics and solve the classical equations of motion, the saddle point equations directly for the matrices. Right? So for large sources, you could try guessing that you can look at the matrix equations of motion, not the eigenvalue ones, right? So I just plug there x and y, and these matrix equations are very simple. They will just give you x minus jx equal lambda y commutator of y of x and y, and y minus jy equal lambda x commutator of y and x. Okay, so that's the equation of motion. I just vary the action with respect to x and with respect to y, and I get these equations. And of course, if I take sources jx and jy equal to 0, a solution of this equation is x equal jx and y equal jy. That clearly solves these equations. This is it, and this is it. And so that would be why, when the sources are very big, the eigenvalues want to go to the eigenvalues of alpha. Now, of course, you could ask, well, but there could be more saddle point solutions and so on. This probably would be the leading one, because if you write that same action as a sum of positive stuff, you see that the smallest positive thing would be exactly the solution I wrote, so that's probably the dominant one. And finally, I want to mention something that is nice in this model, that I don't know if it's something crucial for holographic models or if it is something nice for holographic models, which is that at large lambda, x and y commute. At large lambda, x and y commute. So the very rough intuition you could imagine is that, okay, the coupling is very big, so that commutator better be small, and so on. That is too fast, as I'm going to explain in a second. But let's just do it properly and see what kind of computation you would do to see that they commute. So let's suppose, for example, that we would consider in any of these examples, or for the vacuum, it doesn't matter for what I'm going to do now, some moment, at that moment, say, is something that contains y and contains, say, 2 y's. So it's not just x to the n, but it's, for example, x to the n and 2 y's. Okay? So this y is Gaussian, so you can just write down explicitly what it is. Just 1 over the partition function, integral dx1 all the way to dxn, this van der Waals square of lambda, exponential minus over 2 sum of xi squared, so the Gaussian part. If there is a huge operator, there would be the huge operator here. Depends on it. And then the fact that we integrate out this y would give you something like sum over I and j, xi to the n minus k, x j to the k, divided by 1 plus 2 lambda, xi minus xj squared. Yeah. So that's the result. And this result, let's continue here. So that's exact. There's no approximation done, not even large n or anything. It is just a true statement. And then that result, now if we do large n, if we take large n, you would say that this result is integral dx dy, the sum over I and j becomes integral over x and y, x to the n minus k, y to the k, 1 plus 2 lambda, x minus y squared, rho of x, rho of y. Okay. But that, you see now, we also use strong coupling. And now this would be localized as a delta function. And this would become some integral of rho of x squared, funny thing to integrate density squared, x to the n with some constant. And so here you see only n appears. There is no k anymore. So that just means that the order doesn't matter. Where exactly you put the x's and the k doesn't matter. So that's the statement that y and x commute effectively at strong coupling. And that allows you to compute the moments of in this way of y, and basically that allows you from x to from rho of x to write any moment for y as well, and so to promote this to a density rho of x and y. And this makes sense at strong coupling. It doesn't make sense at finite coupling, but at strong coupling, I can talk about the joint distribution of eigenvalues of x and y. And that density is just an hemisphere. So it is just some universal density that would be just an hemisphere. If rho x is a parabola, rho y is an hemisphere, and you would restore spherical symmetry and get this universal density. Okay, very good. So this you could also do with the general density index. Okay, so now I'll go back. So that's the general thing. So what I'm going to do now is just show you a few pictures. So this was an example. So we worked it out in all detail. What happens when we have one particular type of huge operator? What did we see? We see that there is some universality regions where the details of the operator don't matter at strong coupling. Only at strong coupling. At finite coupling, it changes with alpha, and you get some interpolation from one to the other. But at strong coupling, somehow there are finite regions where things are universal, and then phase transitions. And things are universal, and the universal distribution are these parabolic distributions, or when we go to joint eigenvalues, they are these hemisphere distributions.
Sorry, a naive question. When you start in the strong coupling regime, can you see the square root of 12 as well? It's like you saw from the small coupling regime, you see that, I mean, alpha equals square root of 12 is special, right?
Alpha equals square root of 12 is special at strong coupling. At small coupling, there's nothing special going on.
But if you start expanding from a regime where you know it's universal at strong coupling and then see that something breaks down again, as alpha gets smaller and you choose square root of 12, do you see that as well?
Maybe you are asking if in perturbation theory, if I can see some sign of some radius of convergence breaking down because of some phase transition.
Yeah, from the other end.
Yeah, as I said, we did not do perturbation theory. We literally just solved it directly in some full region. There could be observables. You mean, sorry, maybe you mean from this side, sorry.
So if you start from.
You expand at large alpha, is there some sign that there will be something going on here? I don't know. We did not study the vicinity of this phase transition. It's a very natural question to zoom in close to the phase transition and see if there is some interesting physics there, but we did not explore that much. Okay, yeah.
If you were considering other ratios of other correlators, other powers of X, wouldn't you get something different?
No.
Something alpha dependent, because the shape of the parabola depends on alpha, right?
The parabola, the size of the parabola depends on alpha.
Okay, it's an scale. Okay, fine.
It's just an overall scale. So normalized moments don't depend on it. It's the fact that there is a region where it's always a parabola. Now it's not the same, it changes, but normalized moments are the same.
It's a universal shape.
So it's universal shape, but yeah. Okay, so since we did a computation, we have the right now to say whatever words we want because the computation is the computation. But you could say that it's a bit like some kind of no hair, that there is a regime where it changes, but in a simple way. It's like the mass. It's only changing in a trivial way. Whereas after the phase transition, it's changing in a non-trivial way. Now you get more details showing up. So it's a bit like some kind of no hair thing in a matrix model. Okay, so now in the remaining
Isn't the density of eigenvalues just for the Wiener problem also actually not a semicircle, but it's stretched? And it's normalization.
yeah, when we say semicircle, it's semi-ellipse.
Right. So you could get this just from a quadratic problem. Sure.
No, I mean, a square root of 1 minus alpha x squared can never become a parabola. It's true that it can become very thin and tall, but it's never a parabola. A parabola is really a different curve.
Oh, yeah.
Okay, so we have a few figures. I'm tempted to jump most of them so that we can discuss the discussion calmly, but let's just go through and see if there's anything that is worth stopping and discussing. So this was just what I was saying before, the densities at weak coupling. There's nothing particularly universal. They interpolate within semicircle to this constant distribution, whereas at strong coupling, you see a bunch of densities before the phase transition, and once you rescale them, they all fit exactly on top of each other. After the phase transition, no, they look different and their shape is different. So there is a universal regime and a non-universal regime. So you can do other huge operators like characters, similar to what were done in Lindblom and Maldacena. Again, the same universal parabolas show up, sometimes more than one parabola. So you can have multi-parabolas, but when you have multi-centers, again, each of them is a parabola. You can have other cases that we don't know how to solve analytically. Here is an example. Instead of putting the eigenvalues uniformly spaced, put n over 2 at minus alpha over 2 and n over 2 at alpha over 2. In a sense, it looks even simpler. Now we cannot solve analytically. It's harder to compute this huge operator, but fine, you can do numerics. So here is the eigenvalues of x and y plotted from Monte Carlo. And and indeed, as expected, as it should be, we can derive analytically that it should be like this. It should be a parabola, two different parabolas. It's not spherically symmetric because we are deforming the operator. And indeed, that's exactly what we get. To derive these analytic results, we use this fluid technology that I mentioned that exists for more general operators that we did not need to use for this simple case. Okay, and you can do more checks that you get these two-dimensional distributions. Then you have these phase transitions. For example, you could put the eigenvalues. Now you turn on two types of eigenvalues, not just Jx, but Jx and Jy. Then we cannot do analytics anymore, right? So I put there Jx and Jy. Now it's very hard to integrate out the matrices and to do things analytically. I have two sources turned on. And on top, it's an example where the source is distributed, this Jx and Jy in some red circle. But the circle is relatively small. And so then what happens, what we are seeing there, that cloud of points is Monte Carlo time. As Monte Carlo converges, it converges to the blob there in the middle. So here it is, you run Monte Carlo and it starts and it thermalizes and now it's the Monte Carlo is good. The blue one takes longer to thermalize. The blue one is the case where the source is a circle that's bigger. And that's after the phase transition. And you see the eigenvalues, they come, there are beautiful movies we have. They come, they collide, they open up and they form some circle, some ring-like distribution. So there is some regime where it's a beautiful parabola and some regime which is much harder that it's not really, that it's a ring. So we call one the black hole phase and the other the non-universal phase. But this is just a name. Yeah, same thing happens. You can have phase transitions where these two black hole-like objects split into two as you separate the eigenvalues or form some other phenomenon. And so finally, in the remaining 3 minutes, so what are the points that we took out of this and what would we like to do next? So maybe one question we would ask is this an important feature of these holographic models, that the matrices commute at strong coupling? So do we like this? Is it something that we would like to keep, to think of this holographic toy model? The fact that the matrices exhibit this emergent commutativity at strong coupling, is it a feature that is somehow nice for some classical limit? Probably yes, but okay, it's probably a feature we would like. Now you could try exploring, going from this model towards more richer and richer models. For example, this extension one is just what we wrote, the Hoppe model with d equals 2 extended to higher dimensions. Instead of d equals 2, take d equals 3, d equals 4, d equals 5. These are what are called Young-Mills matrix models. And you could ask, these models, again, when d equal to 2, it's what we just discussed, are they natural extensions? Do they now give three-dimensional shapes of commuting eigenvalues and so on? And the answer is no. So that's an example where these matrices do not commute at strong coupling. At strong coupling, it is not true that moments of commutator square are much smaller than moments of anti-commutator square in this model. Only when d equal to 2. When d is bigger than 3, it's not. Okay? And the intuitive reason is the following, is that when lambda is very big, you would say, oh, I dropped the masses. Right? That's the naive intuition. But in d equals 2, you cannot drop the masses. If you drop the masses, the model doesn't converge. But in d equals to 3, you can drop the masses and the model still converges. And so since you can drop the masses, just rescale lambda away and you get some action of order 1. Okay? So it's about thinking that without masses, you could think this is dangerous because there are flat directions when the matrices commute. But you have to carefully analyze what's the volume of that region where the matrices commute. And if it's low dimensional, it's a big volume and you cannot drop the masses. But if the volume is big, it's fine. It's okay to have some region where the matrices commute and the integral is still convergent, and therefore the matrices do not commute at strong coupling. This second model we really like. We are a bit puzzled by this funny model. I think it's a very cute model. So this is a model where I have 3 matrices, X, Y, and Z, and some simple interaction, Z commutator X, Y. So this is a very cute model that if you integrate out Z, you go back to the Hoppe model. So if I integrate out Z and compute moments of X and Y, it's the same as what we were discussing. Okay? And so, for example, when we integrate out Z, we will get this hemisphere for X and Y. And then I can restore the distribution of X, Y, and Z by just going 1 dimension higher, and it's a beautiful sphere, uniform sphere. So these have a uniform sphere of eigenvalues. Now, and the matrices commute all with each other, because if I integrate out Z, X, and Y commute, I know, but I could have integrated out anyone, so it's 3 matrices that all commute with each other. But this is a funny model because there is no I here. You see that these are Hermitian matrices, so this is anti-Hermitian, so this is a phase. So this model is kind of amusing that there is a phase here. It's a model that you can solve analytically because you can just integrate out the matrix Z and then compute moments, but you cannot solve on a computer. As if you try to put this on a computer, good luck. There is this phase and then it's full of sign problem. So it's strictly speaking non-unitary, but when you integrate out one matrix, it becomes the Hoppe model. So it's not a mistake. It's crucial that there is no I. If there was an I, you would get the Hoppe model with the wrong sign. It would not come in. It's just a fun model. Okay, so this is a model with this but. The but is because it's not unitary. Yeah, this morning the but had the same size, but then during breakfast, Arish and I were trying to find some clear thickness of this model, and we could not find, so I decreased the but. Maybe it's just a good model. I did not find yet any correlator that is negative and it should not be or something like that. So maybe it's better than it looks. Then we have other models like these IKKT matrix models and so on that they have observed the revival. So they were very well studied many years ago, and recently the group of Hartnoll and Leo and the group of Penadon, Adrian Martin, and Shota Komatsu and collaborators, they have revived the study of these matrix models, and in particular studying localization in these models. And we believe that these models have this commutativity at strong coupling. That probably in those models, the commutators of the matrices indeed go to zero at strong coupling, but we don't know for sure. It's a complicated model. It's not like you can just do Monte Carlo. You have like 10 bosonic matrices, you have lots of fermions. It's very hard to do numerics. Adrian, one of the students of Jean, found some lower dimensional versions of this IKKT. So these are matrix models, for example, that look like the first line with say 4 matrices plus a bunch of fermions. And those could be very nice toy models. And in particular, something nice happens with those models is that the Pfaffian that you get when you integrate out the fermions is positive definite. And so it's a model that should be very good to simulate bosonically. And we already started simulating it with Andrea. We only managed to go to sizes of matrices of size 10 or something. It's not enough to see anything. As I told you, there, because of these funny powers of lambda, to see any strong coupling, we wanted to take huge lambdas, huge n's. If you take n equals 10, it's going to be a struggle to see any. And of course, we could go to higher dimensions and so on. So I think it's important, something that I've been trying to do. I mean, just this morning, we were chatting with Juan and Arish about it. I think it's important to understand better the sphere in n equals 4 super-Young Mills. We always think a lot about ADS, or at least I do, about putting things in ADS and throwing things in ADS, and we draw pictures of ADS, and the poor sphere is typically ignored. So I think it would be important to think more about the sphere. How do I prepare things that are separated in the sphere? How do I prepare some wave packet that is in the sphere and something is in the North Pole, something is in the South Pole, and I study things. And I think it's important because that's what we have in matrix models. In matrix models, we don't have the luxury of this ADS to separate things. There's no space, there's no time, so we better develop some more intuition about how to deal with this R charge and how to use this R charge to localize things in faraway regions to be able to see what is the analog of this decoupling of states, what's the analog of having these massive modes and massless modes and the decoupling of those and so on. So that's something I'm quite interested in exploring more. Also the bootstrap. Some of these models, like these quantum mechanical models, have been studied by Andrew Lee and Zexuan Zhang, for example. And it would be very nice if we could develop some bootstrap techniques for these matrix models. And one obstacle we are facing that everyone we tell thinks it's a triviality that we are probably just not smart enough is that is dealing with fermions. So it's when you have these fermions and you want to impose positivity, it's hard. Okay, and I know that if I tell you, that come on, it cannot be that hard. That's what everyone tells us, but okay, we did not manage to do it yet. And of course, it's important to know if we should care about these fermions. Yeah, so we are exploring this. This is the only thing we use AI for, to generate this picture. So we have n equals 4. It seems to be related to Hoppe model. This higher dimensional Young-Mills theory seems to be a bit detached. They don't really commute. This Hoppe model is kind of a toy model for these polarized IKKTs. If we increase dimension, we have BMN. We have this space of models that we are trying to understand if we can study their space, perhaps with bootstrap, perhaps studying other models, trying to understand what is the key feature that distinguish models that have gravity duals from models that don't. Okay, thank you.